Hello, my name is Pavel Maksutin, and I'll be talking to you about detecting COM and ALPC requests. I like to research the Windows internals, how to bypass patchworks, how Warbird works, how can you intercept something in the TCP/IP to be able to intercept network requests. And I also do protectors, like team lead protectors, and one of them. And for 4 or 5 years, I'm working on improving the competency of positive technologies in this area. So how do sandbox systems work? The executable is launched in an isolated environment, and then the log or trace is recorded, and this trace is sent to the correlation engine, and based on those correlation rules in the engine, we can do predictions, detections, and stuff like that. So most of the expertise is built on the system calls, creating processes, accessing registry, creating files, all those, system calls. And this approach has its pros, like you cannot bypass the system calls intercept, because the perpetrator could call something lower level if you use something higher level. But there are also cons, because things like RPC are very hard to relog and monitor on that low level. And this is what I'm going to be talking to you about today. I will start with WMI, and many of you know what it is. It's a Windows administering tool that is based on the object-oriented approach to provide you with required data. And an important thing is that WMI requests are using RPC as a protocol. And perpetrators love WMI because it's easy to abuse. There's a lot of classes to work with the OS. And second pro is that all the WMI requests, any command you send through WMI, will be run in the context of another process, which is WMI post provider service. And if you use Proxmox to monitor the registry access by WMI, you'll see there's no direct correlation between PowerShell and the host provider process that is created. The same applies to running processes, launching processes. It will be launched from WMI host provider service or by it. And if you don't monitor WMI activity, then the attacker can easily bypass all the correlation rules. And those WMI requests can be detected by scanning command lines, CLI. You can also run WMI through PowerShell. You can use specific utilities or run some C code. Thus, the approach to detecting those calls should be comprehensive and high quality. So WMI uses some classes to manage system resources, and they have some interesting namespaces. I'm showing you root SIM-v2 namespace that has everything for working with hardware, journaling, classes to read the information from BIOS, network adapters, physical memory, and all those classes are used quite often to detect virtual machines and sandboxes. There are also namespaces like root default that has classes for working with the registry. And of course, there's a question on how do we detect all that, and I know one way to use GetW, which is a tracing mechanism built in Windows, ETW, And ETW components are listeners, senders of events, and controllers. There's a lot of senders, like I have Microsoft Windows WMI activity provider, and clients can create specific sessions, add their senders or providers, and get the events in real time. So I found the event number 23, which is logging the process creation through WMI. You see command line that was used to launch this process, its ID, and the most important is the client ID. So the ID of the process that sent that WMI request. And this can be used to correlate the client and the process launched. ETW has an issue. It's an asynchronous mechanism, and so if you are an antivirus vendor or EDR vendor, it's a huge issue, because you should prevent the creation of a process, not just learn that the process has been launched. And also, not all classes are supported by ETW. Like I found something for launching the process, but some others might not have specific events. And also, if you take the provider ID and try to trace it to the DLL where it's implemented, we see that the DLL is loaded in the client PowerShell process. And we know that everything that the client is loaded will be patched. Like if you can patch MC, of course you can patch any DLL. There's also Google Project Zero authored project with a set of tools to analyze the sandboxes. And it actually has a custom-coded RPC runtime implementation based on system calls. This means that if you log RPC processes through ETW, then this library can be used to avoid sending you any events, because this library has no ETW event senders whatsoever. And this is not the first time we are encountering the perpetrators who use this library specifically for this. Of course, this is not limited to WMI. All those commands are using RPC, like creating a service, shutting down the system, creating task, MSI, archive, launch. By the way, they are launched implicitly through some service. So to detect such commands, we need a comprehensive approach. And we need to start this talk with discussing what RPC is. RPC is an interprocessor communication process that allows you to launch procedures remotely under different processes. So this standard was created in 1993. Since that, Microsoft, based on this standard, has created their own RPC implementation called MS-RPC. They added some features like authentication using NTLM, some data structure support like strings. And currently, this protocol is very deeply integrated in Windows and is used in pretty much all the components of Windows. It also has a client-server architecture. So here's a diagram of how two processes use RPC to communicate. And for the process, the call of the remote procedure it doesn't differ from the calling of internal procedure, because it just calls the substitute that is porting or proxying the arguments sent and RPC server information to RPC runtime lib. In Windows, it's RPC runtime 4 DLL. This DLL is connecting to the RPC server, serializing the arguments, and choosing the protocol to send them through, and gets all the responses. So it's the same on the server, but just the opposite order. And the protocols for data transfer are plentiful. We see just some of them on the slide, and you can actually say that they are divided into the ones that are targeted at connections or connection-oriented, like IP UDP protocol, for example, and ALPC. And all the local RPC requests today, apart from just some very specific, are using ALPC protocol. And we will be talking about it more in detail. So let's talk about the way those servers work. So RPC server has an interface that has a set of methods that you can call, and each server has one or many interfaces. It's described in a C-like language called IDL, Interface Definition Language, and it consists of the header and the body. So the header has all the attributes, like unique ID, version, because there can be a number of versions, and the body has the method description. So function names, inputs, outputs, return values. So based on the MIDL file, there is a client-server code that is compiled by MIDL compiler, and as a result, you get three files: client stub, server stub, the skeletons for client and server, and a common header file that is used by both of them. So those files are linked to client's application and the server application. So to call an RPC method, the client needs to connect to the server. In a simple case, if we know the protocol that the server is using and the name of the server, here's how it looks. As you can see, RPC method call doesn't differ from just calling a function. But if you have a look at where this function is looking, it looks into a generated file in the middle compiler that just proxies the arguments into the NDR client 03. And that function, the function of which is the function of RPC runtime, receives the arguments. The second argument is the procedure number, meaning it's an index of the function array in the interface, and the first number is the number of function in the interface. So it has all the information you need to connect to the RPC server. Interface ID, version, protocol to be used, and the way to serialize the parameters past the arguments. On the server side, it's a little bit simpler. Server should tell us which protocol it uses and what its name is. It tells it to the RPC runtime library, and it registers an interface. that will be available for connection. It's all done through RPC runtime library. Then it needs to register with the endpoint mapper. We'll talk about it a little bit later, but for now,
Пока что каждый интерфейс, который зарегистрирован,
each interface
он хранится в глобальной переменной внутри RPC runtime
that's registered with the server is stored in a global variable that's stored in the library. So some utilities that enumerate the RPC servers running, they just read that library
там находится.
and parse the structures that are there.
Собственно, интерфейс, который
So the interface
использует сервер, он так
used by the server is very much similar to the client interface,
находится информация по
with the sole difference of having the handler
непосредственно выполняя
for the functions that run the RPC requests themselves.
И, как я уже говорил, с
And as I said,
помощью
same as with WMI, you can trace RPC calls, RPC messages.
которая очень похожа
You can do it using RPC mon, which looks very similar to process mon.
можно
It
посмотреть
also has the filters.
запросы между клиентом.
You can have a look at all the RPC requests between client and server.
Видно,
First of all, the server, you see that the server calls the RPC endpoint mapper and
что он
tells it
такой-то, такой-то интерфейс.
that it supports this or that interface. Then the client, that for some reason doesn't have the name,
К
would connect
определенному
to the server
и
through a specific interface and
видно, что сервер его получает.
create a call. And we see that the server receives it.
RPC
To tell you the truth,
чем показано,
RPC requests are many, and there are many more than I've shown on the picture, but you cannot get them using ETW.
про сервис
And
маппера
a couple more words about endpoint mapping servers,
хранит информацию о
which stores the information about
интерфейсе, который они поддерживают.
RPC servers running and the features it supports.
Так и
It works on both ALPC port and
сетевом.
port 135, the network port.
Запускается как
And every time that the server is launched,
точнее, он, чтобы к нему могли подключаться, он регистрирует
to enable connections, it registers
и затем
within the endpoint mapper,
которого, например,
and then the client
айдишник интерфейса
that, for example, only has the interface ID would ask the service
сейчас запущенный, который этот
for the name of the server that is running, that supports that interface. And the endpoint mapper would return
потом клиент.
the name of the server that the client will use to connect.
Собственно, давайте на примерах посмотрим, как
Let's have a look
выглядит.
at the examples of how
На примере посмотрим, как выглядит RPC-запрос, например, с
some real RPC requests can look.
share.
We'll use NetShare utility.
Монитор, видим, что PowerShell запускает
Let's have a look at the process monitor.
это же
We see that the PowerShell launches NetShare, then it launches net1.exe, and we see the share display all function that calls the netshare enum function. We see it's implemented in the other DLL, and we go there,
и видим, что эта функция тоже
and here's what we see.
заглушка над end.
This function is just
Сайтов мы знаем, что
relay to NDR client 03. So we know that the second argument is the number of the procedure
которая будет вызвана. И
that will be called,
мы можем достать,
and the first argument we can
который
use to get the RPC interface that will be used.
дальше.
So if we trace further,
Берем функцию NDR send receive, и в этой
we'll
функции уже
get to NDR send receive function that has the RPC request
реализованными аргументами
formed inside of it. So it's a packet with all the serialized arguments, whom do you send it to, and if we trace further,
ALPC send wait receive port.
we'll see anti-ALPC send receive port is a system call,
И, собственно, конечная остановка RPC запрос.
and that's the endpoint of our RPC request.
Существует список RPC интерфейсов.
There's a list of RPC interfaces.
ID-шник. Можно поискать там ID-шник.
You can use it to find the interface ID,
Найти по номеру функции,
use the function number
которая
to
все обрабатывает, и найти endpoint.
find the name of the function and find the endpoint
Непосредственно обрабатывает RPC запрос.
that processes the RPC request.
SRV, DLL.
In this case, it's SRV, SVC, DLL.
Какое-то время в песке мы так и делали. Мы
And for some time, we've been doing this in our sandbox. We were just intercepting all the client call functions, not only them, of course, but also other functions. And we took
интерфейс, информацию,
the interface
номер,
info from it,
который
the
называется, и
procedure number that is called, and we're logging them.
лог получался примерно следующий.
The
Здесь
log would look like this.
темп, то есть время, когда это
There's a
произошло,
timestamp,
процесса, его ID-шник,
process name, PID,
и номер процедуры.
and the most important is the interface
Запросов,
and the procedure number.
там тоже были какие-то проблемы.
So it worked for
Говорить, но
the RPC procedures,
захотим
RPC interfaces, and
COM запрос,
but there were some issues. I won't be touching on them
потому что
today. But if we want to log the COM requests,
и если мы
and
перерабатываем на этом уровне,
that won't work because it is
интерфейс
constructed above the RPC, and things like
может содержать
interface ID
невалидные
would contain invalid data
без какой-либо обработки не
that you will not be able to parse without
Собственно,
customized processing.
COM интерфейсы. По сути,
So, speaking about COM interfaces,
плюс-плюс это C с классами, так и COM это
as we said, C++ is C with classes, so COM is RPC with classes.
ему нужно
So, for an interface to become a COM object, it needs to be inherited from iNone, and it implements three functions: query interface and the link counter to this object. Yeah, interfaces can be
в примере я наследую
inherited.
iDispatch интерфейса и
And I'm actually
особенный, потому что он позволяет,
using iDispatch here
не зная,
to create my interface because it allows
например, имя
me, without knowing the procedure number, to call it just by name,
name,
like
получить
using get IDs of name, get procedure ID, and then with using invoke
этот
function,
полезен, например, если
I can call this function based on the name. It's useful, for example, if the RPC server has updated, some methods were added, and the client was not updated,
имя функции, которую он хочет вызвать.
but the client knows the function name that it wants to call.
Появился класс,
Also, we have
есть уникальный тоже
a class
этот
that has unique ID
RPC интерфейса.
that implements the RPC interface.
Информация о всех зарегистрированных COM-объектах
And the info about all the COM objects registered is in HK classes root registry, CLS ID
утилиты
entry, and using OliView, for example, you can have a look at all those classes,
имена, то есть
find the names,
человеческое название этих COM-объектов, посмотреть
the real name, the kind of readable names for those COM objects, look at the endpoint, the library or executable that implements this object,
глянуть.
and, for example, interfaces.
Собственно, COM-объекты
So, COM objects
двух видов, они могут хранить
can be of two different varieties. They can be stored in DLLs
клиент.
or
На
XF.
самом деле, когда
The
подгружается DLL
simplest form,
объектом,
when the client
использует RPC
uploads the DLL with COM objects, it will not be remote calls. It will just be local calls to the classes and methods like in C++. But in the case where the COM object is implemented in the servers, then the client would call the endpoint mapper and launch the server if it's not launched, and return to the client the so-called proxy object, which would marshal the calls to the server. And at this point, we need to talk about LPC, ALPC, to tell you about how all those requests are mapped to the system calls, to the ALPC level. So a couple of words about ALPC. It was LPC originally, local procedure call, inter-processor interconnection protocol. Then starting with Windows Vista, it changed into advanced LPC, ALPC, improved version, that has asynchronous data transfer functions, shared memory usage, some kind of security functions. And same as LPC, ALPC is not documented, but based on the previous works and presentations, we know how it works, roughly. So even if you don't use COM and RPC, any process would be connected to at least one ALPC port. ALPC port is a core object that is stored in the RPC control directory of objects, and it has a name. Not all ALPC ports are stored in this directory, like the ports that are just not used for ALPC calls can be just stored in root. But ALPC is stored in LPC control directory. You can actually easily understand which port is used when you see OLE, the beginning of the ALPC port name, then it's used for COM requests, COM calls, and all the other are RPC calls. And actually there are 3 ports. The server would also create a named connection port that has a name, and you can connect to it. And by knowing this name, the client can connect to the ALPC port. And in this moment, if the server has accepted the connection, maybe it has some security protection, access control, then 2 other ports are created, the client port and server port. They have no name and they are used by the client to send ALPC packets, and the server would use its port also to send ALPC packets. The structure of the ALPC port is shown on this slide. It's quite complicated, but we only need 3 fields. Communication info that stores the pointers to all 3 port objects, the current process that, owner process that this port belongs to, and then which port it is, connection port, client port, or server port. There's many LPC calls and requests. One RPC request, one RPC call would have 4 or 5 LPC packets. So if you intercept them and you don't filter them, then it would load the system very significantly. So you can use this field to filter only client LPC requests, for example.
Структура LPC пакета.
The structure of the ALPC packet is so the functions inside the package allows to both send and receive packets, and each packet would start with a specific header, port message, where you can see the client ID. You have the ID and TID of the client there, and at the ALPC request sending time, they are not valid, so the system would fill them later when it arrives on the server, so they are not of interest. But the amount of data and overall size of the packet are very useful fields that would show the size of the packet.
If we look at how ALPC packages look, then we'll have this structure. First, you have ALPC message, then you have RPC message, inside of which, in case if it's COM request, then it's COM message, COM headline, and then arguments. If it's RPC, then the serialized RPC follow the RPC headline. Serialization of arguments is going to stay away from this presentation today. It's quite an extensive topic, but actually there are utilities, and it's clear how to decode these arguments, and it's not big hustle. So let's take a look at the example that was in the RPC section, and let's see how it is compatible with ALPC protocol. Disclaimer, I used WinDebug for a more vivid representation of how it looks. And we see that the first request contains interface ID, and the request will be sent there. Then there's a response from the server, and then some procedure gets called T35L5, 1337. These are arguments that are being passed. Also in this package, you can find the procedure number that's being called. So you can see that for one RPC request, there are 4 ALPC packages. The first package, that is bind, it is necessary to get connection between the client and the RPC server. In other words, any package, any RPC package, any RPC package starts with a headline which indicates the type. RPC packages have quite a lot of types. We're interested particularly in 3 of them, which is request, bind, and response. Let's start with bind package. There are presentations about RPC, and it has this bind structure, but I'm showing a little bit a different structure. There are fields here, version 20 bind ID, other bind ID, and non-binding ID. I will talk about them a little bit later. In this package, in bind package, we're interested in 3 fields only, even 2 fields. It's interface ID, the ID of the interface that the client gets connected to, and identifier syntax. Identifier syntax is actually a field which is the client sends, and it indicates the protocols are maintained there, which the ones that are compatible. For instance, on the slide you can see 3. So the client supports a version 1.2.0 protocol and NDR64E. It is sent to the server, and the server already chooses one of the protocols itself. And based on this protocol, a binding ID is used. So if you look at the system call that happens in case of bind request, then you will see the argument to receive and to send packages is the same. And in case if we look at the difference between the packages, then you will see that client send that it supports these two protocols, and the server or the processing unit says, okay, I want to talk in this protocol. So the client takes protocol 2.0 version and took a binding ID that identifies the protocol. So this binding ID is further used during request packages, and the describer is ALPC port, and you can see what RPC interface is being requested, and in the request package you can see the number of procedure and lower you can see arguments that are being transferred. COM requests. Disclaimer, in order to make it more indicative, I will be showing a log from WinDbug because, as I said, there are a lot of them, and in this case, it's going to be more indicative. So, once we create instance objects, we indicate the class where this interface, where this object is used, and the interface itself. In the traffic, we can see two requests. The first request is bind request with COM object interface, and the second request is request with the procedure number and with some ID that we're going to talk about a little bit later. It looks like 4 ALPC packages, but actually there are much more of them, many more. First, there are a lot of requests to endpoint mapper, so that endpoint mapper would download COM object, so the service. Then it has, on the slide you cannot see this, but there are also verifications there, rights verification, ALPC service. Also, there are Windows Defender checks, and you can see that before the connection to ALPC port will be established that COM does. You can see that from endpoint mapper, there's received a package of quite a large size. And in case if we look inside this package, then we will see that endpoint mapper returns serialized objects or COM object to the client. This object is described by object ref structure. It has a special headline, meow. In the package, there are always present 2 objects. First one is not very interesting to us, but the second one stores information about this object, COM object. In COM, when client and server are interacting, there are a few interactions: EPID, OXID, and EE. OXID is ID of the unique interface ID of the endpoint mapper. It's not interesting to us, I didn't show it here. And PIT is a unique IP GUID of RPC server. So COM has classes, and it has not only methods, but it has variable classes. And in order to when COM object is being created, then the server creates a unique entity of this COM object in order to
Ну ладно, не чтобы.
Well, okay, not in order to.
И ID интерфейса — это ID.
And interface ID is the ID of the interface that we want to get connected to.
Это интерфейс.
In this package, an interface is ID's patch.
И тот
And the ID that was in the request package, and it was in RPC, ARPC headline. This is a PID of this interface, and you can see that this is what the client is referring to.
Ну, для справки хотелось
If
показать.
you look at, well, just for your information, I wanted to show what functions are actually called, because by the numbers, you cannot see that. You can see that first it gets connected to endpoint mapper, then it checks the rights, I guess, then it creates the object once again, then checks the rights again, then two functions, ID by name and call by ID. And what I want to mention here is the binding ID role. I mentioned it earlier, based on endpoint mapper. You can see that client gets connected to 4 interfaces of endpoint mapper, and binding ID is the number that's implemented when the client gets connected to one of the interfaces. You can see that first there are 4 connections, so binding ID will be 3. Then there's the 5th connection, and right after that, a call from binding ID 4. So you can tell clearly which RPC interface the call goes to. And in conclusion, if you call COM object not by the real interface but through ID patch, then you will see that ALPC traffic, the real interface, is not showing anywhere. And the only life hack of how to work around it, I found how to correlate it, at least in some way, correlate the call of COM request is to get the ID class of the COM object that interface is running, and you can get it from current DAB. It's a special field reserved for OLI, and there it is. For instance, intercepting RPC requests, you can just find this field and log it. In the end, I'd like to show a few examples just to prove the truth of what I said. WMI request from the start. Launching the process through N32 process class, Win32 process class. With these 2 lines of PowerShell, we have 105 ALPC packages. Also, Windows Defender was disabled here. This is why there will be actually more packages, because Windows Defender also scans MC interfaces and checks something else. And it refers to 8 different endpoints. And based on these endpoints, you can see that some got logged into event log. I guess it requested access rights to the object. And in the end, there is the endpoint that processes the COM requests. Out of all these requests, what's interesting to us is the connection to interface call IVBM level 1 login. It can be obtained from response package to endpoint mapper. You can log it. In this package, there is interface ID. You can log it. You can get IP ID, which is unique IP on the server. And class ID is WMI mitigated here. Then there is connection to IVBM services. Package response once again, but it's not endpoint mapper now, it's endpoint COM objects. It's logged, ID of the interface is logged, it's unique ID of the interface on the server. You can see that CLSID is 0. It's not valid anymore. It's not used anymore. So we take this IPD and we correlate it with the request package to this interface. The first request package is to create a class. As you can see, or as I said, WMI uses classes, and the class that works with processes is Win32 process. In this package, in this request, it is created, and the function is object. And in the package, you can see name of the class. Then there is a call of the method from this class. It's done by exec method function. And in this package, you can see command line of the process run. You can see the object, well, not the object, but the class by which this method is launched. And you can see the name of the method, and you can see the previous packages that I mentioned about. It's not necessary for correlation, but in order to understand what it's about, I included this. I hope it explains it. And the very last one, how to detect COM requests, but not COM, but RPC requests. It's very easy. We should look for a bind request, and we log interface ID and binding ID, then correlate binding ID the request, and we log the number of the procedure number. I hope it's clear. And in the very conclusion, I'd like to say that in case if you have any questions that you will not be able to ask me today, you're welcome to reach out to me in a DM message. And also, please follow Escalator. Escalator has a lot of great life hacks and notes how to do great things. That's all that I have, and now we can switch to Q&A session.
Надеюсь, всем все понятно было.
I hope I explained it well, and it was clear. I was making myself clear. Oh, I can see hands raised in the back rows.
Спасибо.
Thank you. Thank you for the presentation. My question is not about detecting, but my question is more about blocking messages of RPC requests. As far as I understand, it's enough to block for the ports 454 and the 135 port, and this way we're limiting any requests to the server using RPC. If you do that, I think that the system will not be working in a stable manner. This port is used for good things, for the benefit. Yeah, and the second question. At the start, you mentioned WMI provider post service. Yeah. How liquid is it to disable this service by default? It's more of a question. Like many, I can say that it's a best practice, but many companies are recommending when we issue recommendations to the misconfigure, then they recommend to disable some services, and WMI provider is one of them. To be frank with you, I didn't even know it's possible to disable it. But I assume that if you disable it, then COM requests will not work. And getting back to system stability, I'm not sure it will help system stability. So if I get it right, it's best to keep them on the network ports and host to services. We just need to set up the detect. Yes, I'd rather do that. Thank you. From the back rows, there were more questions. Hello, thank you for the presentation. I have a few questions. And the first one may not even be from your domain, but I work with RPC sometimes. When you start coding, you take the file, it's compiled, you get the on H files points, and it redefines the structure from Windows.h, for instance. Is there any method in order to manually keep the structures but not to delete them because there's an error in the compilation? Haven't you seen this?
Пару предложений повторить.
Could you repeat the last few sentences? Just the microphone is not working well. From MIDO, compilator is providing C and H files, and in the H file, there are some structures that are determined as Windows.h, and it causes an error. How do I overcome it? Because there are two definitions there. It's a great question. I've never seen this. I'm afraid I cannot answer this question. Okay, we just delete it manually, and it's not very convenient. And about registration, RPC service on the client, it's not as necessary to register it in the endpoint mapper. So these are dynamic endpoints. But in case if we put it on the known the service, we can use without IP mapper. In case if the name of the protocol is known, it's okay not to register it. Also, you mentioned that EP mapper returns object ref, but it's not EP mapper. It's if RPCSS should do this, right? EP mapper, RPCSS server is engaged there. So they're passing to one another. Okay. And my last question, is there any difference between login mechanism depending on how RPC server works? There is implicit, explicit bindings. Are they different? Could you repeat the question? There are implicit and explicit bindings. Even one flow, many flow interaction, and the mechanism of login, does it differ depending on that? No, it doesn't. And by the way, I mentioned that beginning from Windows Vista, ALPC protocol is being used, but I have seen cases that ALPC system requests still trigger traffic running. It's the same as with ALPC, but the other system calls. I guess it's legacy of RPC servers. All right, thank you.
Привет, спасибо за доклад. Я здесь.
Hi, thanks for the presentation.
У меня вопрос с точки зрения мониторинга. Насколько понимаю, ты рассказывал.
My question is about monitoring. You mentioned a sandbox specificity, but my question is about domain. We have APC filters that are set up into commands. You just need to know the ID and the RPC of the server that you want to monitor, and it's enough to roll this out this way. In terms of coverage of events that we get, this approach that you described, is it better? Or do these two approaches complement each other? I could say that my approach is better, but I see that for some it doesn't work, it's not good. For instance, antivirus don't intercept system calls, it's more for the sandbox, but using events log in order to log RPC and COM requests is a valid technique, but you should expect that those people who want to work around it, they can easily bypass it. They can bypass logging the request. Okay, thank you.
Добрый день, спасибо за доклад.
Hello, thank you for the presentation.
Правильно ли я понял, что
Do I get it right that monitoring technique is based upon the following? With an ETV collector, we just review what is going on with RPC, right? Yeah, in traffic.
Другими словами,
in other words, well, I worked with it a little bit, but have you seen problems of performance? Because it's a nightmare. Too many requests and performance is not good. You have to filter them in the app when you already received everything, when everything has been... Yes, I've seen it. And I can't talk about the solution, but the solution is available. Yes, there is a solution available. You can, first of all, you can filter RPC packages in advance. For instance, to use, you can log only client, because we don't know what this. It's not. We don't want to know what the server responds, but we want to know what the client was requesting. Also, you can pre-filter the type of packages. You can use only 3. You can log RPC bind, request, and response. So it should be done on the level of collector in the core, right? Yep. All right. And one more question. You even highlighted it, that if the criminal wants it, then the criminal can use an alternative realization, or he can patch something. But haven't you thought about obtaining data with the help of Windows filtering platform? Because it has some filters that could Windows filter platform in the core. You can request the core itself to log ALPC requests or ALPC calls, and it looks like a super reliable remedy, because whether you patch it or you don't patch the client or the server, whether or not it goes through the core, then you will get the telemetric data anyway. I have not done it. Maybe you have done it. Maybe you have code and it will be amazing. I have not done this as well. And I have always been thinking that WPP uses ETV under the hood. So events are retrieved from there. But I'm not sure about that. I'm not knowledgeable about this. But let me keep it in mind. I will look into this. It's interesting. Yeah, it would be great. And maybe some code somewhere. Is there a code somewhere? No, there is no code there. And I'm not sure whether it will be there. It's not for me to decide. Anyway, thank you very much for your great work. Thanks for the question.
Очень мало времени, поэтому если у вас быстрый вопрос.
No, we don't have much time, so we have a quick question. Then go ahead. Thanks. I wanted to build upon the question about disabling WMI. If we're talking about the client's machine, is it going to be great? Isn't it going to be smooth? And about managing in terms of information security and IT, does it influence the opportunity of GPO rollout and other things that are managed on the level of domain? Also, can we granulate control when WMI is enabled? One of the examples, when domain administrator installs software for console management in order to get connected to user session, things like that through WMI. To be frank with you, I don't know, so I cannot give any recommendation here.
Давайте я футболку вручу, вот мужчина.
Let me give the gift to this man with great questions. The T-shirt is yours. Thank you very much. That's all that I have.